Hi everybody. Today we are going to review the whole idea of the limit and how to compute different types of limits. So this is in correspondence with the Unit 1 of AP Calculus AB, or if you're just taking a regular calculus course, this would be your first unit on just limits before derivatives and integrals. So let's just start with a little background. So as we know, for any function, we have a domain. So let's just start with a simple function to get warmed up. So f of x is equal to x, for example. So we can graph this. So let's just graph this really quickly. And we'd have a graph something like that. So this is our f of x value. This is our f of x is equal to x graph. So this is the x-axis and this is the y-axis. So we can say that for this function is defined for all, so f is defined for all x, for all x. What does that mean? So like any real number that you put into this function, say like negative pi over 2, or like pi squared over 3, or something like that, or like even 200 billion thousand million or something like that, or negative that thingy. So all of those are valid inputs for this function. So we can say that the domain of f of x, so this is how you write it, is it exists, x can be any real value. So all of those numbers which I stated, like pi, or negative pi, or negative square root 3 over 2, everything falls under this real number category. So, or you can just write this as x is any real number. Or you can use interval notation. So interval notation would be negative infinity to positive infinity. And we use parentheses because infinity isn't really a number, so we never reach that value. So it's like a limit which we never reach. So we have to use the parentheses. If we had, like, say, a discontinuity and like something else, we would also use our interval notation as that, as we will soon see in a moment. So this is a fully continuous graph at every single point. Now let's look at a different example. Okay, so say we have another function g of x. Let's just use a different color. Say we have g of x is equal to the function x squared minus 9 over x minus 3. So let's just graph this really quickly, shall we? So we can draw our axes. And then this is actually a function which we can take the limit of pretty easily at x is equal to 3. So this has in the denominator, if we put x is equal to 3, we get a 0, and we know that we cannot divide by 0. So let's just see what would happen to this graph. So we'll just graph this really quickly. Okay, so this is our graph. And let's just say that we have our let's just try to get to 1, 2, 3. So that's x is equal to 3. But at that point, we actually have a discontinuity. So instead of having a full, it would be an open dot. So an open dot. Right? So this is at what y value? This is at the y value 6, as we'll soon see. So this is basically just equal to the function x plus 3, but x cannot equal to 3 because if you were to actually graph x plus 3, then this would be closed instead of open. But we want it to be open, so this is not the same thing. And we'll learn about this when we learn how to compute the limit analytically or algebraically. So what is this thing? So what if we wanted to write the domain of this function, the domain of g of x? Well, the domain would just be equal to x is any real number except x cannot equal to 3. Or if you were to use interval notation, you could just write it as negative infinity to 3 and parentheses because we never have anything at real 3. And then parentheses again, and then positive infinity, close parentheses. So this would be the interval notation. This would be your other type of notation if you wanted to write it. You can write it in either way. You wouldn't get any points deducted. Okay, so this type of a discontinuity, what is this type of a discontinuity? So this type of a discontinuity is actually called a point discontinuity, and it's also known as a removable discontinuity, as we will soon see how to remove it. So we just removed it for this one. If we were to actually simplify this as the difference of squares, so this would be x minus 3 times x plus 3 over x minus 3, you would just get x plus 3 here, and that would close that dot, removing the discontinuity. And we will soon see how important that is when we solve for the limit. So there are two more types of discontinuities, which we will see now. So let's get h is equal to, so the function h of x is equal to, say, x over x. We'll just write this in a small graph. Oops. And then have a long thing here. So here we would have, oops, so let's do this in blue. Okay, so this is at -1 and this is at +1. So, and this is the graph. You can look at this on your graphing calculator, but this is how it looks like. At 0, there's a jump discontinuity. There's like a jump, right? So here also, it has a similar domain as the last one. So the domain of h of x is equal to x can be any real number except x cannot equal to 0, or like the same interval notation. Right? So any of these are the same. And this is called a jump discontinuity. So jump discontinuity. And it looks like a jump, right? Or sometimes it might go from up to down, so it's still called a jump discontinuity. And we'll just remember these names. And we'll do one more graph, I of x, which is equal to 1 over x. And you might have seen this graph many times before, but let's just see it one more time. Okay, so it looks something like that. Something similar to that. So here we have a horizontal asymptote here and a vertical asymptote here. So that means it never touches x is equal to 0. So here we have a discontinuity at x is equal to 0. So the domain of oops, wrong color. Okay, so let's just write this in white. So the domain of I of x is equal to x is any real number except x cannot be equal to 0. It's just the same exact thing as for h of x, and the same interval notation. You can just take note of that. So this is called an infinite discontinuity, and it makes sense, right? Because on one side you're going up to positive infinity, and on the other side, on the left side, you're going down to negative infinity. So it's an infinite discontinuity. Okay, so now we'll continue. So now that we know all the types of discontinuities, which are, just think of them again, a point discontinuity, which you can remove somehow by simplifying, a infinite discontinuity, and a jump discontinuity. Okay, so now let's get to the idea of a limit. So what is a limit? So the limit is the the value that a function at, say, f takes, or approaches, I should say, that's a better word for this, approaches at a certain x value from, and keep in mind, both sides, the left and the right side, okay, of that x. So what does this mean? So say we had our graph f of x, our handy dandy f of x graph. So say I wanted to take the limit, so this is the notation. You have lim, and then x approaches, say, 1. So we have x is equal to 1 here, of f of x, or just write x. You can write it as f of x, which is equal to x, or you can just write it as that x as the function. And we want to see what value this is approaching as we get closer and closer to 1 from both sides. So closer and closer to this point right there. So as this might be obvious, this is equal to 1. And so like for any continuous function, if you know that a function is continuous over its whole domain, all real numbers, or at least around it and at it, if it's continuous at the point, or like if it's continuous around the point, then you can just say that the limit as x approaches c for f of x is equal to f of c for f being a continuous over near domain of x, okay? So near x, it has to be continuous. Otherwise, you would have to do something else to do it. So that is, and another important point is that if and only if the value approached by the left and the right sides is equal, does the limit exist. Otherwise, then like in a jump discontinuity, say like you're from -1 at one point and you just go straight to +1, there is no limit at that point there when it jumps from -1 to 1, because how does it approach one singular value? You have two different values there, so you cannot really do anything. So we'll do that. So now we're gonna do a graphical finding the limit. So for any continuous function, so we already discussed this, at least around the x value, we have to approach the limit. We can find it really easily if it's continuous around there. So if we have, say, the limit as x approaches 3 of x squared minus 6x plus 9, we know that this is a continuous function. Therefore, we can just plug in this 3, we can plug in the 3 into where x is. So we get 3 squared plus minus 6 times 3 plus 9, which is equal to 0. So the limit is just equal to 0. Because it's continuous, we can just make it equal to that point, okay? So you can also do this graphically, and you will find that it is equal to the same exact thing. Let me just draw this graph really quickly. This is actually supposed to, yeah, better. So it touches the x-axis only at that point. So this is equal to 0. So that confirms that the limit is the same. Okay, so now let's just try to do another limit. Okay. So say we want to find the limit as x approaches 0 of the absolute value of x over x. We already saw this one, so let's just draw this really quickly. So it's just this is -1, this is +1. So this is the graph of it. Okay, so it's a little slanted, but okay. So here we have a jump discontinuity. So I already said that we cannot find the limit here, but let's just try. So we can when we're doing this, I said that only if the left and the right side are equal to each other. So let's find those left and right side. So this is called the one-sided limit. So let's just do it from the negative side, from the left. So then we write it as x approaches 0 from the negative side, because all the values on the left are less than it, so it's a minus of this function, and it looks like we're approaching -1, and this is +1. So this is equal to -1. Now let's compute the limit as x approaches 0 from the positive side of this same function. And it looks like we're approaching +1. So is -1 equal to +1? No, it's not. Therefore, so this is the mathematical notation for therefore, the limit as x approaches 0 of this function does not exist. So this just simply stands for does not exist. So you can, if it doesn't exist, you can just write DNE, and that will give you full points. Okay, so same thing for an infinite discontinuity. If you had 1 over x, then because on one side it's going to -infinity and the other side is going to +infinity, so also the limit as x approaches 0 of that same function does not exist. And we can just look at that graph once again. So we have this graph, right? So as we approach 0 from the left and then from the right, it's going down to infinity, -infinity on the left side, so that would be 0 minus, and 0 plus, it would be going to +infinity. Therefore, we can see that because +infinity and -infinity do not exist, I mean, you can write them as do not exist. So the limit itself does not exist. So for an infinite limit, a limit that is equal to infinity, you can either write it as infinity or does not exist, or -infinity or did not exist. It doesn't matter. Either one will give you the same credit. But if you see here that -infinity and +infinity do not equal each other, so also it does not exist in that manner either. So it would give us the same limit. Let's continue on. Now that we're done with the graphically and like understanding how to compute the limit, let's do it algebraically. So say we have to compute the limit as x approaches 2 of x squared minus 5x plus 6 over x minus 2. So let's just try to do this directly substituting. We don't know if this is going to be continuous at 2 or not, but let's just try this out. So we get 2 squared minus 5 times 2 plus 6, which is equal to 0. And then 2 minus 2, which is also equal to 0. So we get 0 over 0. We cannot divide by 0, though. So this is called an indeterminate form. Indeterminate form. And if you get any indeterminate form, that means we have to do something else to try to find the limit. And as you can see here from algebra 2, or algebra 1 also, this is a quadratic function which you can easily factor into x minus 3 times x minus 2, and then over x minus 2, and we're still computing the limit as x approaches 2. And these two cancel out, so we get the limit as x approaches 2 of x minus 3, and then we can directly substitute it, and we get 2 minus 3, which is equal to -1. That is our limit. But here, there's a really important point we have to remember. This does not mean that this function right here is equal to that function right there. X minus 3 is not equal to x squared minus 5x plus 6 over x minus 2. Because here, x minus 3 is continuous at x equals 2. But this other function, with the x minus 2 on the denominator, is not continuous at x is equal to 2. Therefore, there is a domain change. Therefore, these are not the same exact thing. Okay, so that's how we can do it by factoring. Now let's just look at another type of algebraic limit. Okay, so let me just clear the board. Okay, so say we have to compute the limit as x approaches 4 of the function x plus 5 minus 3 over x minus 4. So if we were to try directly substituting, we would get 4 minus 4, which is equal to 0 on the denominator side. And from the numerator, we would get 4 plus 5, which is equal to 9. The principal root of 9 is equal to 3 minus 3 is equal to 0. So we would get 0 over 0. So we cannot do a direct substitution. So this method, when we have a radical, and you cannot directly substitute, we use rationalization. So radicals, they have a conjugate. You just switch this sign, basically. So, and then we just multiply this whole thing by its conjugate over its conjugate. So, and we'll see why this is so useful. So let's just write this down, the conjugate. So it would just be plus 3 instead of minus 3. And we have to divide it by itself because then we would get 1. And we can just multiply it with the numerator and the denominator. And if we see here, this is a difference of squares. We would just get the square root of x minus 5, x plus 5 squared, which would give us x plus 5. And then negative minus 3 squared, which is equal to 9. And then over in the denominator, we'll just leave this unexpanded. We have x minus 4 and then our conjugate. Okay, so this is just equal to x minus 4, which we can then simplify into asking us what is the limit, just like what is the limit as x approaches 4 of 1 over x, the square root of x plus 5 plus 3. And then if you directly substitute this in, you get 1 over 6. So it's a really cool way to solve things with rationalization. Okay, so now we'll just go to trig, solving trig limits. So trig limits is pretty straightforward. So we know that there are 6 main trig functions, right? What are those? You can think of those like sine x, cosine x, and tangent x. You only really need to know these 3 because the other 3 are just the reciprocals. So 1 over sine x is equal to cosecant x, 1 over cosine x is equal to secant x, and 1 over tangent x is equal to cotangent x. So if you know the values for these things, you would know the values for these things because you would just do 1 over that value. So because sine and cosine are basically just the same thing, right? They're always continuous. We can just say that the limit as x approaches c of either sine x or cosine x is just equal to sine of c or cosine of c. So, but for tangent x, it's not always continuous, but you can, for whenever tangent is continuous, then you could say that then the limit as x approaches c for tangent x is also equal to tangent c. But for some values like pi over 2, it's not because sine over cosine is equal to tangent, and cosine at pi over 2 is equal to 0, whereas sine is equal to 1, so 1 over 0 leads to undefined. So not always it's not always going to be continuous. Okay, so now we're going to go to limit rules. So let me clear the board here. So what are the different limit rules? So there is the sum rule. So let's start with that. Say we wanted to find the limit as x approaches c of f of x plus g of x. Well, this is pretty straightforward. You would just write it as the limit as x approaches c of f of x plus the limit as x approaches c of g of x, and that would just be the limit. This is the sum rule. Now let's do the difference rule, which is basically the same idea. Or we can just write this in one simple thing. So this is the sum and difference rule. So if it's a plus, then it would be a plus. If it's a minus, then it would be a minus. So those two go together. So that is the sum and difference rule. And now for the product rule. So the product rule states that, let me write this in white. Okay, so the product rule states that if we have limit as x approaches c of f of x times g of x, then this would just be equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x. So really just straightforward. And for the quotient rule, it's also the same exact thing. If we have the limit as x approaches c of f of x over g of x, this is equal to the limit as x approaches c of f of x over the limit as x approaches c of g of x. So these are the four main rules. And there's also one more rule which is really important, which is called the composite rule for composite functions. So let's just take a look at this. Composite functions. Composite functions are of the form f of g of x. So if you wanted to take the limit as x approaches c of f of g of x, this is just equal to f of the limit as x approaches c of g of x. Or you could just say this is equal to f of L for L equaling to the limit as x approaches c of g of x. Okay, so now let's just head on to the squeeze theorem, which is a pretty hard to understand, I think, for some people, but it's just a really easy concept. But we have to use this for many different applications. So let's just say that we have this function h of x, which is greater than or equal to f of x, but less than or equal to g of x. So it's in the middle of that at all times. Let's just draw a graph and look at this. So basically, what this theorem states, is that if h of x is always between two functions, and those functions are equal at some point, then that means that definitely, because it has to squeeze through, that function has to squeeze through, therefore it is equal to that point as well. Like in this example, here we have x squared and negative x squared, and we have this sinusoidal function. Because x squared and negative x squared are equal to 0 at x equal to 0, that means that this sinusoidal function also must be equal to 0 at x is equal to 0. Therefore, we can state this in limits. So if the limit as x approaches c of f of x is equal to the limit as x approaches c of g of x, which is equal to the function L, then that means that by these standards, the limit as x approaches c of h of x is also equal to that same L. Right? So they are the same exact function. Because, they are the same exact value at that point. Because, say here, they have to all be equal to the same value. They can be equal. And because f and g are equal, that means that because this is always in the middle, h also must be equal. That is the squeeze theorem. And from the squeeze theorem, there are two limits which we can, trig limits, which are extremely important for the test, which you must memorize. And if you would like to see how we compute this, you just memorize them. If you want to see how you compute them, you can check out the video on the squeeze theorem on this channel. So these are the two main special trig limits. So we're almost done now. Or cosine x minus 1 over x is equal to... Okay, so these are the two different limits which you can memorize. Either of those would be equal to the same function, same value. Okay, so now we are going to discuss two different things, the last two things. First one being the IVT. the intermediate value theorem, which is extremely important and very useful in applications. So the intermediate value theorem states that if f is continuous over the closed interval a, b, right? So if it is continuous over a and b, and k, we have a value k now, which will be in blue, is a number between f of a and f of b. So let's write that down. And f of b. Then there must be a value c within a, b. I'm not going to use the colors right now. Such that f of c is equal to k. So this might seem really ridiculous. What are these words saying? But it's really easy to understand. So we just need to look at a graph to understand this concept. So say we have, this is a and this is b. This is f of b and this is f of a. So that means we can draw a graph here connecting this point. So let's just say it's continuous, right? So like we can do something like that, which is continuous. It's a cool function there. But like, say we pick any random k here. There has to be a way for some x value to equal k. X value such that that value, the f of x value at that point is equal to k. Otherwise, it should not be continuous. So see here, there is a c that equals f of c is equal to k. But what if we had to make sure that it does not equal to k? How can we do that? Wrong color. So we have a, we have b, we have our curve, and let's just pick our k value. This is our k value, which we want to skip. So we start at b and we end at f of b. Okay, so to do it, we have to somehow skip over it by like having a discontinuity, or like have an infinite discontinuity, or something like right there. But somehow there has to be a discontinuity. It can be a jump discontinuity, for instance, but somehow or the other, it has to be discontinuous for it to skip over k. Otherwise, it has to include k. So this is a continuous graph. This is a discontinuous graph. So that's the IVT. And you can use this to find zeros in the bisection method, which you won't really need to know for AP Calculus. But it's pretty good to understand it. So basically, you just have this interval and say this is where our 0 is. We can find what half has the 0 in it. What half has the 0 in it. And then we will be able to find it by just bisecting it until we get to that 0. Okay? So there is one last thing. So I'm going to erase this. There's one last thing we need to understand about limits. And this is the idea of a limit at infinity. So if we have this function, say right here, right? At infinity, as we go closer and closer to positive infinity or closer and closer to negative infinity, the limit as x approaches infinity of f of x is equal to positive infinity. And if it was at limit as x approaches negative infinity of f of x, it would be equal to negative infinity. So that's straightforward. Let's just get that straight. Oops. So let's just erase that really quickly. Okay, so now we will try to do this algebraically. Say we have to take the limit, let's just change the color. of this pen. Okay, so the limit as x approaches infinity of, say, x squared plus 3 over x plus 1. And I'll write two more. X approaches infinity of x squared plus 2x squared plus x plus 1 over 3x squared minus x plus 2. And one more, the limit as x approaches infinity of x to the third power plus x to the second power minus x over x minus x to the fourth plus 1. So we're going to find these three limits algebraically. So when you have something at infinity, you can just cross out everything which is not the highest degree in here. So these are the highest degree terms. In this one, these are the two highest degree terms. And here, this is the highest degree in the numerator, and this is the highest degree in the denominator. So let's just try this out. So we can simplify this to be equal to x, and as we know, x just approaches infinity because it gets bigger and bigger and bigger. So if the degree of the numerator is greater than the degree of the denominator, d stands for degree, not to be confused with the denominator inside of the parentheses, then the limit as x approaches infinity of f of x is equal to infinity. However, what if the degree is the same? And in here, the degree is less. Well, in this case, the degree is the same, so we just divide it, and we get 2 over 3. So the limit as x approaches infinity of such an f of x would be equal to, say this is a, and say this is b. These are the coefficients. It would just be equal to a over b. In this case, a is equal to 2 and b is equal to 3, so the limit is equal to 2 over 3. And finally, if the denominator has a higher degree than the numerator, then we would just be left with, like, say, negative 1 over x. And as we can see of that graph, it would be like that and like that. And it approaches 0. So for such a function, the limit as x approaches infinity of f of x is just equal to 0. So these are the three different types of infinite limits, which you can see. These are all when limit x approaches positive infinity. At negative infinity, it's a little more complicated, but we won't really need to worry about that. So today we learned about what the domain of a function is. We learned about how to find the limit. What is the limit? How to find it at graph, from algebraically, and like rationalization, factoring, trigonometry, limit rules, the composite function, and the squeeze theorem. We also learned the sine of x over x and the 1 minus cosine x over x, those two squeeze theorem trig limits. If you want to learn how to compute them, you can look at our squeeze theorem video. And also the IVT, the intermediate value theorem, which is extremely important. It's a type of an existence theorem in calculus, which is similar to, let's say, the mean value theorem, which you will learn later after derivatives, which states that there has to be some x value which is equal to a y value within the range of f of a and f of b if the function is continuous. And this has really useful applications like the bisection method. And the infinite limit, as is shown on the screen, how you can compute the limit as x approaches infinity of any function, basically. So thank you very much for watching, and have a nice day. Oh, and one last thing about infinite limits. If you have something about, like, say, trigonometry, say the limit as x approaches infinity of sine of x, this does not exist, because sine of x always just oscillates. So you're not ever sure when it would be equal to -1, when it would be between -1 and +1, and when it would be equal to 0, when it would be equal to +1. So therefore, it does not exist. Same with secant, cosecant, tangent, cotangent, and the cosine. So any trig limit at any infinite value just does not exist. So that is all. Thank you. Hope you guys do well on your Unit 1 test. of AP Calculus, and wish you all best of luck in your studying. Thank you for watching, and have a nice day.